Hi, I'm Anne. I am presenting chance-constrained multi-robot motion planning under Gaussian uncertainty. Consider an exploration scenario with areas we want to investigate while avoiding obstacles. We are interested in motion planning for a team of robots, which offers better coverage, is more efficient, and can have diverse capabilities. But motion planning for even deterministic kinodynamic teams is very difficult. We add motion and sensor uncertainty, making planning even harder. So what are useful existing techniques? Let's start with basic sampling-based motion planners, and especially tree-based planners. These are some of the most ubiquitous deterministic methods in motion planning because they are both fast and adaptable. Recent work introduces Gaussian belief trees, or GBTs, which extend tree planners to robots with linear models and Gaussian motion and measurement noise. So GBTs are great for single agent planning, but what about robot teams? Well, the naive approach would be to compose all the robots into a single meta agent, and then use a single robot planner with the composed state. This is a coupled approach with an exponentially growing search space, meaning it scales terribly. More scalable approaches leverage decoupled planning, like kinodynamic conflict-based search, or KCBS, a multi-level search algorithm. Plans are generated independently for the robots in the low level using a single robot planner. The high level checks for conflicts between robots, which are stored in a constraint tree, then passed to the low level planner for replanning. This framework leverages the speed and efficiency of single agent planners and is generally agnostic to the choice of low level planner. However, it is a deterministic planner. So where does this leave us? We have a scalable multi-robot planner with KCBS and an uncertain single-agent planner with GBTs. But we have no planner that can do scalable motion planning for uncertain robot teams with safety guarantees. This leads to our algorithm, chance-constrained KCBS. Our planner generates motion plans for all the robots while respecting safety constraints on both obstacle robot and robot-robot collision probability. We make the simplifying assumption of linear motion and measurement models with Gaussian noise. Our solution, CC-KCBS, leverages the two existing methods, deterministic multi-robot KCBS and the single robot uncertain GBTs. This planner not only provides safety guarantees, but also scales very well and inherits the completeness properties of the low-level sampling-based planner. The most difficult part in adapting KCBS for GBTs was formulating the probabilistic robot-robot collision checker. So why was this hard? Let's start with how you calculate the probability of collision. For simplicity, say we have a translating point robot in a 2D space with a Gaussian state distribution. The probability of collision with a deterministic obstacle is found by integrating the probability mass over that obstacle. Now consider that our robot has a body and can rotate. The probability of collision is the integral over the collision states. For a given orientation, this is the Minkowski difference. However, we need the probability of collision for any orientation, each corresponding to a Minkowski difference. This results in a three-dimensional integration area. However, in our problem, the obstacle is actually a second probabilistic robot, so we need to form a six-dimensional integration area of the Minkowski difference for both robots. This is impractical, and even if we could construct it, evaluating over the joint Gaussian belief is intractable. To address this, we propose approximate validity checking techniques. These are called at every iteration in the sampling-based planner, so they must be very fast. And to guarantee safety, they must be sound. With this in mind, we propose three different methods, all of which are sound because they use over-approximations. The simplest and most conservative checks for intersections between spheres. The second method applies existing linear constraint checking with a polytope bound, where the complexity scales with the number of constraints. And the most computationally intensive and accurate method uses grid integration, where the complexity scales with the number of grid cells. The computational complexity and conservatism do play off each other. We ran benchmarks to characterize this for each method. We sampled sets of belief and then applied our approximate methods. We used Monte Carlo sampling to evaluate the true collision probability. The conservatism is the rate of false negatives. Note that because our method is sound, there are no false positives. The benchmarking results are shown here, with conservatism on the left axis and computation time on the right axis. The x-axis corresponds to different proposed validity checkers, which decrease in conservatism as they increase with computation time. Now let's get back to the bigger motion planning picture. The results table here shows performance for each collision checker in a small, empty environment. The collision checkers decrease in conservatism across the columns. We examine success rate and computation time as more reagents are added. See that the more conservative collision checkers on the left side of the table quickly fail to find plans as the number of agents increases and the space becomes cluttered. However, the less conservative planners are also more computationally intensive, and as the number of robots increases, the computation time becomes prohibitive, and the planner begins to time out. With this in mind, we use the simplest collision checker to push scalability in more open environments. We were able to scale to 20 robots in an obstacle-filled environment and 30 robots in an empty environment. Through Monte Carlo sampling, we found that the total trajectory-wise probability of collision was less than 2% when the point-wise probability constraint was set to 5%. Our experiments have demonstrated scalability, and our paper provides proofs for the soundness of collision checking. This establishes CC-KCBS as a powerful algorithm for multi-robot teams under uncertainty. Thank you.